Imagine you're about to step into a race, but before the competition even begins, you need a starting line. That's where we are today. Before we dive into the complexities of machine learning, neural networks, and decision trees, we need to talk about the simplest yet most essential starting point, ZeroR. Now you might be thinking, wait, why should I care about the simplest model? Because, my friend, this is where every great data science journey begins. Imagine you're a detective working on a case, and before you start looking for clues, you just guess the most common crime in your city. That's what ZeroR does in machine learning. It makes no attempt to learn patterns. It simply predicts the most frequent outcome. And here's the kicker. Sometimes that's enough to give you a surprisingly strong benchmark. But here's the real question. If your fancy, complex machine learning model can't beat ZeroR, do you even have a good model? Think about that for a second, because in just a moment, we're going to unravel why this seemingly primitive algorithm holds the key to understanding and evaluating every model that comes after it. Ready? Let's begin. Machine learning is all about making predictions, but before we get into complex models, we need to ask a simple yet crucial question. How do we know if a model is actually good? That's where ZeroR comes in. It's the simplest classification model imaginable, and while it doesn't look impressive on the surface, it plays a fundamental role in evaluating machine learning performance. ZeroR doesn't try to be smart. It doesn't look for patterns, relationships, or hidden insights. It does one thing. It finds the most frequently occurring class in your dataset and predicts that for every single case. That's it. No learning, no decision making, just the simplest possible prediction. At this point, you might be wondering, why would I ever use such a basic model? The answer is simple, because it sets the baseline. If a fancy machine learning model can't beat ZeroR, it's a sign that something is seriously wrong. Either the data lacks useful patterns, the features aren't meaningful, or the model itself isn't performing as expected. Think of ZeroR like a rookie basketball player who never moves but always takes the same shot because, statistically, that's where most successful shots happen. If a highly trained player performs worse than this stationary shooter, you'd question their skill, right? The same logic applies in machine learning. ZeroR acts as the absolute minimum level of performance, and any model that fails to beat it is simply not useful. But there's a twist. Sometimes ZeroR is surprisingly effective. In highly imbalanced datasets, where one class dominates, ZeroR can achieve a deceptively high accuracy. Imagine a medical dataset where 95% of the patients are healthy and only 5% have a disease. A ZeroR model predicting healthy every time would be 95% accurate, yet completely useless at identifying sick patients. That's why evaluating models requires more than just looking at accuracies. So before we dive into complex algorithms, let's first explore how ZeroR actually works, because if you truly understand this simple model, you'll never look at machine learning evaluation the same way again. To truly understand ZeroR, you need to step into its simplicity. It's not trying to compete with complex algorithms, nor is it concerned with uncovering patterns or making sophisticated predictions. Instead, it serves as a minimalistic benchmark, a way to check if your data and models are even capable of doing better than the most basic approach possible. Let's break down how ZeroR operates step by step. The first step is constructing a frequency table. This is the foundation. Imagine you're given a data set. Let's say it's about customer satisfaction, and your target variable includes responses like satisfied, neutral, and dissatisfied. ZeroR doesn't look at features like age, income, or product type. It only focuses on the target variable and counts how many times each class appears. The result is a frequency table that tells you the exact distribution of responses. This simple table holds the key to everything ZeroR does. Next comes identifying the most frequent value. Once the frequency table is built, ZeroR scans it to find the class with the highest count. In our customer satisfaction example, If 65% of customers chose satisfied, this becomes the majority class. This class will serve as the single prediction for every instance in your dataset. ZeroR assumes that the most common outcome is the best bet, regardless of any additional information. Now, with the majority class identified, it's time to set the prediction rule. This is where ZeroR's simplicity becomes almost absurd. It predicts the majority class for every single instance, no matter what the input data says. Let's say you're trying to predict customer satisfaction based on features like purchase frequency, location, or customer complaints. ZeroR completely ignores all of that. It doesn't care if the customer had a bad experience or left a scathing review. It will still predict satisfied every time because that's the most frequent response. It's not trying to be right, it's just playing the odds. Finally, we reach the critical step, evaluating model performance. This is where ZeroR reveals its true purpose. By calculating its accuracy, ZeroR gives us a baseline performance metric. If 65% of customers in the dataset are satisfied, then ZeroR achieves 65% accuracy, nothing more, nothing less. This baseline acts as the minimum bar any other model must clear. If your sophisticated machine learning model, with all its complex calculations and features, can't beat ZeroR's accuracy, then something is seriously wrong. Perhaps your features don't actually add value, or maybe your model is overfitting to noise in the data. Either way, ZeroR exposes the problem. But there's an interesting twist here. In some datasets, ZeroR can seem deceptively good. For example, in highly imbalanced datasets, like medical diagnoses where 95% of patients are healthy and only 5% are sick, ZeroR could achieve 95% accuracy simply by predicting healthy every time. While that sounds impressive, it's a disaster if your goal is to identify sick patients. This is why accuracy alone isn't enough to evaluate models. ZeroR reminds us to dig deeper using metrics like precision and recall to understand true performance. By following these steps, constructing a frequency table, identifying the most frequent value, setting a prediction rule, and evaluating performance, ZeroR establishes itself as a critical tool in the machine learning toolbox. It may not be flashy or powerful, but its role as a baseline is indispensable. It forces us to confront the question, is my model actually adding value, or am I just overcomplicating things? And now that we know how ZeroR works, let's explore why its simplicity can be both a strength and a limitation. But first, let's talk about the advantages it brings to the table. ZeroR might seem overly simplistic, but that simplicity is exactly what makes it so powerful in certain contexts. It's not trying to solve the world's problems or uncover hidden patterns. It exists to provide clarity and a solid starting point for understanding your data and evaluating more complex models. Let's explore why ZeroR is not just a basic tool, but a foundational one for machine learning workflows. The first advantage of ZeroR is its simplicity. It's the most straightforward classification model you can imagine, requiring no complicated algorithms, no hyperparameter tuning, and no data pre-processing beyond counting occurrences in the target variable. It doesn't care about predictors or relationships between variables. All it needs is the target variable. This simplicity makes ZeroR incredibly accessible, even for beginners who are just starting to learn about machine learning. You don't need to be an expert in algorithms or optimization techniques to understand how ZeroR works. It's as easy as looking at the most common outcome. Another key advantage is its ease of implementation. ZeroR can be set up in minutes, often with just a few lines of code. It's the definition of low effort, high clarity. This is particularly useful in the early stages of a project where you might be exploring the dataset and trying to get a feel for its structure. By establishing a baseline with ZeroR, you can quickly determine whether your data even has predictive potential. It lets you focus on more advanced methods without getting bogged down in complex setups too early in the process. If ZeroR performs better than expected, it's a clue that your data might be imbalanced, or that simple rules govern the outcomes. The third advantage lies in its role as a performance benchmark. ZeroR provides a baseline accuracy against which all other models must be compared. If a model you're testing performs worse than ZeroR, it's a clear sign that the model isn't capturing any meaningful patterns in the data. For example, let's say ZeroR achieves 70% accuracy on your dataset. If a decision tree or neural network fails to surpass that, you'd immediately know there's either a problem with your model or your data. ZeroR forces you to question whether your more complex solutions are genuinely adding value or just adding noise. ZeroR is also excellent for prototyping and testing. Imagine you're working on a tight deadline and you need a quick way to evaluate your dataset or test an idea. ZeroR allows you to skip the overhead of designing complex models and instead focus on the bigger picture. It's particularly useful in situations where speed is a priority, such as initial presentations or exploratory analysis, because it provides actionable insights without requiring significant computational resources. ZeroR is also excellent for prototyping and testing. Imagine you're working on a tight deadline and you need a quick way to evaluate your dataset or test an idea. ZeroR allows you to skip the overhead of designing complex models and instead focus on the bigger picture. It's particularly useful in situations where speed is a priority, such as initial presentations or exploratory analysis, because it provides actionable insights without requiring significant computational resources. In summary, ZeroR excels in its simplicity, ease of use, and ability to serve as a baseline for comparison. It's a tool that grounds your analysis and helps you identify what's meaningful and what's not before diving into more advanced techniques. While it's not the solution to every problem, it's a vital part of the journey toward understanding your data and building better models. And while the advantages are clear, no tool is perfect. Next, we'll explore the limitations of ZeroR and why it's rarely used as a standalone solution. While ZeroR serves as a fundamental starting point and a reliable benchmark, its simplicity comes with significant drawbacks. As much as it helps ground our understanding of a dataset, it is not designed to solve real-world problems. Let's dig into why ZeroR, for all its usefulness, is limited in scope and application. The first and most glaring limitation is its lack of predictive power. ZeroR doesn't analyze input features at all. It completely ignores them. Its only focus is on the target variable, which means it fails to capture any relationships or patterns in the data. For instance, if you're trying to predict customer churn based on features like product usage, customer satisfaction, or service complaints, ZeroR will give the same prediction for every case, regardless of these factors. This makes it incapable of delivering insights or actionable predictions. Another major limitation is its inability to handle complex data. In the real world, datasets often contain intricate relationships between multiple features. Consider a medical dataset where factors like age, symptoms, and test results interact in subtle ways to indicate a diagnosis. ZeroR doesn't even attempt to analyze these complexities. It simply predicts the most frequent outcome. As a result, it produces oversimplified conclusions that fail to capture the nuances of the data. This makes it unsuitable for tasks requiring detailed or accurate predictions. The third drawback is its limited use in practical applications. ZeroR is rarely a viable solution outside of its role as a baseline. Think about applications like fraud detection, credit scoring, or medical diagnoses. In these scenarios, accuracy and precision are crucial, and relying on ZeroR's blanket predictions could lead to disastrous outcomes. For example, predicting not fraudulent for every transaction might yield a high accuracy in an imbalanced dataset, but it would fail to identify actual fraud cases, rendering the model useless for its intended purpose. There's also the issue of bias in imbalanced datasets. In datasets where one class dominates, like a medical dataset where 95% of patients are healthy, ZeroR can achieve deceptively high accuracy by always predicting the majority class. However, this comes at the expense of completely ignoring minority classes, which are often the most critical to identify. This bias makes ZeroR a poor choice for scenarios where minority classes carry the most importance, such as predicting rare diseases or identifying fraudulent transactions. Finally, ZeroR doesn't provide any insights into the data. Unlike more advanced models that can highlight feature importance or uncover trends, ZeroR offers no interpretability beyond the frequency of the target variable. It's a static, one-dimensional tool that cannot answer deeper questions about why certain outcomes occur or how changes in input features might affect predictions. In summary, while ZeroR is invaluable for its role as a baseline, its limitations are clear. It lacks the sophistication needed to handle complex, nuanced, or real-world problems. It's not designed to provide accurate predictions or insights. It's a tool for comparison, not a solution. And this is why it's critical to understand ZeroR's boundaries before relying on it in your analysis. Next, we'll look at how ZeroR compares to other classification models, diving into the strengths and weaknesses of these more advanced approaches. Now that we've explored ZeroR's simplicity and its limitations, it's time to put it in perspective by comparing it to other classification models. ZeroR might set the baseline, but when stacked against more advanced algorithms, the differences become clear. Let's explore how ZeroR holds up and when it starts to fall short. ZeroR operates on a single principle: always predict the most frequent class in the dataset. For instance, if 70% of your data falls under class A, ZeroR will predict class A every time, achieving an accuracy of 70%. This simplicity makes it computationally efficient. ZeroR doesn't require any training or fancy computations. It constructs a frequency table for the target variable and predicts based solely on that. Compared to other models, this lack of complexity means ZeroR is fast, lightweight, and easy to implement. But that's where its advantages end. Let's bring in a decision tree for comparison. Decision trees use input features to split the dataset into meaningful subgroups, finding patterns and relationships within the data. While ZeroR blindly predicts the majority class, a decision tree might uncover that customers aged 25 to 34 with high purchase frequency are more likely to churn, or that patients showing certain symptoms are at higher risk of disease. This ability to capture feature interactions means decision trees typically achieve much higher accuracy, sometimes over 85% or more depending on the dataset. However, they require more effort. Feature selection, parameter tuning, and computational power all come into play. Now let's take it a step further with models like neural networks. Neural networks are designed to handle highly complex datasets, using layers of interconnected nodes to learn subtle patterns that other models might miss. For example, a neural network could analyze thousands of images to identify features humans can't see, such as microscopic signs of disease in medical scans. This sophistication comes with trade-offs. Neural networks are resource-intensive, requiring extensive training on large datasets, and can be prone to overfitting if not carefully managed. Still, they're miles ahead of ZeroR when it comes to predictive power. Even simpler models like logistic regression or k-nearest neighbors outperform ZeroR. These models use input features and mathematical techniques to find patterns and relationships. For example, logistic regression might show that a customer's churn probability increases with certain behaviors, such as late payments or frequent complaints. ZeroR, by contrast, offers no such insight. It doesn't even look at the input data. The key difference between ZeroR and other models lies in their ability to leverage features. ZeroR doesn't use features at all. It's oblivious to the data's structure and patterns. Advanced models, on the other hand, thrive on these details, using them to produce not just accurate predictions, but also actionable insights. But there's one area where ZeroR has an edge: simplicity. Advanced models can be overkill for small or unbalanced datasets where accuracy is heavily skewed toward the majority class. For example, if you're working with a dataset where 95% of instances belong to a single class, even a sophisticated model might not outperform ZeroR by much. In these cases, ZeroR provides a quick, no-frills way to establish a baseline without wasting time or resources. Ultimately, ZeroR's role is to set the floor. It answers the question, what is the bare minimum level of performance we can expect? From there, other models aim to raise the bar, delivering better accuracy, interpretability, and functionality. ZeroR isn't meant to compete with these models. It's meant to provide context for their success. Next, we'll dive deeper into how ZeroR interacts with data, starting with the process of constructing a frequency table, the foundation of its predictions. Now let's dive into the mechanics of how ZeroR gets started, constructing a frequency table. While ZeroR's predictions are incredibly simple, this step is critical because it lays the foundation for everything the model does. It's a straightforward process, but it provides valuable insight into the distribution of your data. Let's explore how this is done step by step. The first step is data collection. You start by gathering your data set and focusing specifically on the target variable, the outcome you're trying to predict. Whether you're working with customer satisfaction, medical diagnoses, or product classifications, the quality of this data is critical. If there are errors, missing values, or inconsistencies, your frequency table will be unreliable. For example, if you're analyzing customer reviews, you'd need a clean and accurate list of responses such as positive, neutral, and negative. This ensures that what you're counting truly reflects the reality of the dataset. Next, it's time to count occurrences. This involves systematically going through the target variable and tallying how many times each unique value appears. For small datasets, this can be done manually, but for larger datasets, say thousands or even millions of rows, you'd typically use programming tools like Python or R. For example, in Python, a simple function like value counts in pandas can generate a frequency table in seconds. The goal here is to determine the distribution of classes, such as how many times each class, e.g. satisfied, neutral, dissatisfied, appears. Once you've counted the occurrences, the next step is organizing the table. This is where you structure the data for easy analysis. A typical frequency table has two columns, one for the unique class labels and another for their corresponding counts. For instance, if satisfied appears 6,500 times, neutral 2,000 times, and dissatisfied 1,500 times, your table would list these values side by side. Visualizing this data, perhaps with a bar chart or pie chart, can further enhance your understanding of the class distribution. This visualization is particularly useful in identifying imbalances, such as one class overwhelmingly dominating the others. At this point, you've built the foundation of ZeroR's prediction. The frequency table doesn't just show you the most common class, it also gives you a snapshot of the dataset's overall structure. If the table reveals significant imbalances, you might already have insights into how challenging the dataset will be for more advanced models. For example, if 90% of the instances belong to a single class, even a highly sophisticated model might struggle to improve much beyond ZeroR. But the frequency table isn't just a tool for ZeroR, it's a vital step in any data analysis pipeline. It gives you a clear, unfiltered view of your target variable, helping you understand the dataset before you dive into more complex modeling techniques. By constructing a frequency table, ZeroR begins its process of delivering predictions based on the simplest rule, always choosing the majority class. Next, we'll see how this table feeds directly into the next step, selecting the most frequent value. Now that we've constructed the frequency table, it's time for ZeroR to take its simplest but most important step, selecting the most frequent value in the target variable. This step is where ZeroR establishes the baseline prediction rule, setting the stage for all its future predictions. Let's break this down. The process begins with analyzing the frequency table. This table, which we've already constructed, lists each unique class in the target variable along with its count. For example, in a dataset about customer satisfaction, your table might show 6,500 instances of satisfied, 2,000 of neutral, and 1,500 of dissatisfied. The key task here is identifying the class with the highest count, the one that dominates the dataset. Once the class with the highest count is identified, the next step is to select it as the predicted value. In our example, the class satisfied has the highest frequency, so it becomes ZeroR's prediction for every single instance in the dataset, regardless of any input features. It's important to note that ZeroR doesn't care why satisfied is the most frequent. It simply assumes that predicting the majority class is the best bet. This decision influences every prediction made by the model. ZeroR operates under the assumption that the most frequent class is always the correct choice. So, in a dataset where 70% of the instances belong to class A, ZeroR will always predict class A, whether it's analyzing historical data or making predictions on new observations. It's a static, one-size-fits-all approach. But what makes this step so impactful is its role in creating a baseline for evaluation. The accuracy of predicting the majority class becomes the minimum standard against which all other models must be compared. For instance, if ZeroR achieves 65% accuracy by always predicting the majority class, a decision tree, logistic regression, or neural network must do better than 65% to justify their added complexity. At the same time, the simplicity of this step is both its strength and its limitation. While it gives a clear baseline, it completely ignores minority classes. For example, in a medical dataset, if 95% of patients are healthy, ZeroR would always predict healthy, achieving 95% accuracy, but failing to detect the 5% who are actually sick. This is why ZeroR is rarely used as a standalone solution. It's a starting point, not the finish line. By selecting the most frequent value, ZeroR locks in its prediction rule, setting the benchmark for other models. In the next step, we'll see how this rule is applied in practice and how ZeroR evaluates its own performance. ZeroR's prediction process is as simple as it gets. Once the most frequent value is identified, it applies this rule universally to all instances. This step highlights ZeroR's defining characteristic, making predictions based purely on the majority class, ignoring all input features. Let's explore how this prediction logic works and its implications. Once ZeroR has selected the most frequent class from the frequency table, for example, satisfied in a customer satisfaction dataset, it applies this as the predicted output for every observation. This prediction doesn't depend on any features or specific conditions. It's a blanket rule. No matter the input, ZeroR will always predict the majority class. If 70% of customers in your dataset are labeled as satisfied, ZeroR will predict satisfied for all instances, regardless of whether the customer left a glowing review or expressed frustration. This approach is not only simple but also inflexible. Let's consider a scenario in a healthcare dataset where 95% of patients are healthy. ZeroR would always predict healthy, completely ignoring symptoms or test results. While this might yield a seemingly high accuracy, 95%, it fails catastrophically when it comes to identifying the minority class, in this case, the 5% who are actually sick. This demonstrates ZeroR's fundamental limitation, its inability to detect or adapt to nuances in the data. However, ZeroR's universal prediction rule has one critical purpose. It establishes a baseline performance metric. By applying this simple rule across the dataset, ZeroR provides a clear accuracy benchmark. For example, if 80% of instances in a dataset belong to the majority class, ZeroR's accuracy will be 80%. This number represents the bare minimum that any other classification model must surpass to be considered effective. If a decision tree, random forest, or neural network performs worse than ZeroR, it's a clear sign that the model isn't capturing meaningful patterns in the data. But the predictive simplicity of ZeroR also reveals a critical gap. It offers no insights or explanations. Unlike more advanced models that might highlight feature importance or relationships between variables, ZeroR's predictions are static and devoid of context. For instance, it can't tell you why satisfied is the most frequent class or how input features like age, income, or behavior impact outcomes. To summarize, ZeroR predicts the target class using one rule: always choose the majority class. This prediction method may seem overly simplistic, but it serves as a foundational benchmark. It forces us to ask the question, can our models truly add value, or are they just complicating a simple problem? Next, we'll explore the real-world implications of ZeroR's predictions and how it measures up against more advanced techniques in real-world scenarios. ZeroR might be a simple model, but it has its place in real-world scenarios. Its primary utility lies in its ability to establish a baseline for classification tasks and provide quick insights into datasets. While it's not a practical solution for complex or nuanced problems, it plays a foundational role in the early stages of machine learning projects. Let's explore how ZeroR is applied in various real-world contexts. One significant application is in initial model assessment. Before diving into complex algorithms, ZeroR helps evaluate whether the target variable in a dataset has predictive potential. For instance, if you're working with a dataset to predict customer churn, ZeroR sets the baseline accuracy by predicting the majority class, such as customer retained. If your advanced models fail to outperform ZeroR, it signals that something is wrong. Perhaps the features don't correlate with the target, or the dataset isn't suitable for prediction. In baseline performance benchmarking, ZeroR is indispensable. Businesses often need to assess whether their machine learning models are truly effective. ZeroR provides the minimum threshold of performance. For example, in sentiment analysis, if ZeroR achieves 60% accuracy by predicting the majority sentiment as positive, any advanced model must surpass this to justify its complexity and implementation costs. Without this benchmark, it's difficult to gauge the success of a more advanced approach. ZeroR is also useful in data preprocessing and exploration. By focusing only on the target variable, it highlights issues such as class imbalances, missing values, or anomalies in the dataset. For example, if one class dominates 90% of the data, ZeroR reveals this imbalance early, prompting you to consider resampling techniques or weighted metrics to handle the disparity. In certain specialized cases, ZeroR can be applied directly, albeit sparingly. For example, in resource allocation, where simplicity and speed are priorities, ZeroR might serve as a quick tool to categorize instances based on majority class trends. In a retail setting, if 80% of customers purchase a specific product type, ZeroR's prediction can guide inventory decisions in the short term. Similarly, in healthcare, ZeroR might provide an initial view of the most frequent diagnosis, offering a rough snapshot of patient trends. However, its most critical role is in guiding practitioners to improve models. ZeroR forces analysts to evaluate whether their features and data preprocessing steps are effective. If an advanced model's performance barely exceeds ZeroR, it's a wake-up call to revisit the drawing board and refine the approach. In summary, ZeroR's real-world applications are rooted in its simplicity and ability to act as a benchmark. While it's not a tool for nuanced decision-making, its value lies in helping data scientists and businesses measure the baseline performance and identify areas for improvement. It's the launchpad for more sophisticated models, ensuring that every machine learning project starts with clarity and direction. Next, we'll move into performance metrics and see how ZeroR helps evaluate advanced models beyond just accuracy. Now that we understand how ZeroR works and where it fits into real-world applications, let's take a deeper look at how we measure its performance. While ZeroR is not meant to be a predictive powerhouse, its metrics provide a valuable reference point for evaluating more complex models. Understanding how ZeroR performs and where it falls short helps us establish meaningful benchmarks in classification tasks. The first and most commonly used metric is accuracy. This is simply the proportion of correctly classified instances in the dataset. Since ZeroR always predicts the majority class, its accuracy is equal to the frequency of that class in the dataset. For example, if 70% of the dataset belongs to class A, then ZeroR's accuracy will be 70%. This gives us an immediate baseline. If a more advanced model doesn't exceed 70%, it's not adding value. However, accuracy alone can be misleading, especially in imbalanced datasets. If a dataset contains 95% class A and only 5% class B, ZeroR will predict class A every time, achieving 95% accuracy, but at the cost of completely ignoring class B. This is why additional metrics such as precision and recall are needed to fully evaluate ZeroR's performance. Precision measures how many of the predicted positive instances were actually correct. Since ZeroR doesn't differentiate between classes and always predicts the majority class, its precision for the majority class is typically high, while for the minority class it's non-existent. It never predicts it at all. Recall, on the other hand, measures how many actual positive instances were correctly predicted. For the majority class, ZeroR's recall is 100% because it predicts it for every instance. However, for the minority class, recall is 0% because it never predicts that class, failing to identify any of its occurrences. To get a balanced view of model performance, we often use the F1 score, which is the harmonic mean of precision and recall. ZeroR's F1 score tends to be misleadingly high for the majority class and 0 for the minority class, reinforcing why it should only be used as a reference point rather than a standalone model. Another valuable metric is the AUC-ROC, area under the receiver operating characteristic curve. This measures the ability of a model to distinguish between classes. Since ZeroR doesn't actually differentiate between them, its AUC score is usually 0.5, meaning it performs no better than random chance. In summary, ZeroR's performance metrics highlight its biggest weakness. While it might achieve reasonable accuracy, it fails to capture meaningful class distinctions. Its purpose isn't to be a strong predictive model, but rather to provide a baseline for evaluating more advanced models. If a complex model only marginally outperforms ZeroR, it's a strong signal that improvements in feature selection, data preprocessing, or model tuning are needed. Now that we've explored how ZeroR is evaluated, let's move beyond its limitations and look at ways to improve classification performance. ZeroR has given us a baseline, but let's be honest, it's not a real solution for classification problems. It ignores input features, makes static predictions, and fails in scenarios where minority classes are important. So how do we move beyond ZeroR and build models that actually add value? The answer lies in improving data quality, model selection, and evaluation strategies. Let's explore the key ways we can go from a naive majority class predictor to an intelligent classification system. The first step is feature selection and engineering. ZeroR doesn't use input features at all, but real models must. To move beyond ZeroR, we need to identify which features in our dataset contribute meaningful predictive power. This can involve removing irrelevant features, selecting the most influential variables, and evaluating feature importance through tree-based methods. Selecting the right features ensures that our model actually learns from patterns in the data rather than just guessing. Next, we must address model complexity and generalization. If a complex model barely outperforms ZeroR, it could be suffering from underfitting by not learning enough from the data, or overfitting by memorizing patterns that don't generalize to new data. To combat this, we can use regularization techniques to prevent overfitting. Apply cross-validation to ensure performance is consistent across different subsets of data, and tune hyperparameters using optimization methods to improve model performance. A significant improvement over ZeroR also comes from using advanced algorithms. Instead of relying on the most frequent class, we introduce machine learning models that learn patterns in the data. Decision trees split data based on meaningful features, capturing simple relationships. Random forests improve stability by averaging multiple trees. Gradient boosting refines predictions by sequentially correcting errors. Neural networks can detect complex patterns in high-dimensional data but require careful tuning to avoid overfitting. Another key improvement is evaluating beyond accuracy. ZeroR often achieves deceptively high accuracy in imbalanced datasets, so we need metrics that provide deeper insights. Precision and recall ensure we capture both majority and minority class performance. The F1 score balances the trade-off between false positives and false negatives. The AUC-ROSI score measures how well the model distinguishes between classes. Finally, iterative model refinement is essential. Machine learning isn't a one-time effort. It's a continuous process of testing, learning, and improving. Implementing feedback loops to learn from model errors, regularly updating models as new data becomes available, and using ensemble methods like bagging and boosting to improve stability and accuracy all contribute to moving far beyond zero. Moving beyond ZeroR means focusing on extracting real patterns from data, optimizing model performance, and evaluating success with meaningful metrics. The goal isn't just to outperform ZeroR, but to build models that make reliable, actionable predictions. Now that we've explored improvements, let's take a practical look at ZeroR in action with real-world case studies. ZeroR might seem too simplistic to be useful, but its value becomes clear when applied as a baseline in real-world scenarios. One such case is customer churn prediction, where businesses aim to identify which customers are likely to leave their service. Before testing sophisticated models, ZeroR provides an essential benchmark to measure whether more advanced approaches are truly effective. The dataset consists of 10,000 customer records, with features such as age, subscription type, and service usage. The target variable is customer churn, which is classified as either 1 or 0, indicating whether a customer has left the service or remained. The first step in applying ZeroR is to determine the most common class. If 75% of customers have remained while 25% have churned, ZeroR predicts that every customer will remain, achieving a baseline accuracy of 75%. With this baseline established, any machine learning model trained on this dataset must surpass 75% accuracy to justify its complexity. If a decision tree, logistic regression, or neural network fails to outperform ZeroR, it suggests that the features being used are not providing meaningful insights into customer churn. This forces a re-evaluation of the dataset, prompting the inclusion of better predictive features such as past customer complaints, engagement levels, or billing history. By comparing ZeroR's performance to more sophisticated models, businesses gain insight into whether their data is truly valuable for prediction. If a model significantly outperforms ZeroR, it indicates that meaningful patterns exist in the data, allowing for more targeted retention strategies. However, if ZeroR remains competitive, it suggests that the data lacks useful signals, requiring further investigation into additional features or alternative prediction approaches. ZeroR serves as the starting point for evaluating predictive models in customer churn analysis. While it is not a solution in itself, it ensures that more advanced models are actually contributing value rather than simply adding complexity. Understanding where ZeroR stands in the modeling process helps businesses refine their approach to customer retention and improve their ability to anticipate churn. Now, let's look at another case study where ZeroR is used in sentiment analysis. ZeroR is not limited to structured business problems like customer churn. It can also be applied to text-based classification tasks such as sentiment analysis. In this case study, we examine how ZeroR serves as a baseline for evaluating machine learning models designed to classify customer sentiment in product reviews. The dataset consists of 10,000 customer reviews from an e-commerce platform, with each review labeled as positive, neutral, or negative. The goal is to build a model that accurately classifies sentiment based on the review text. Before jumping into complex natural language processing techniques, ZeroR is applied to establish a baseline. The first step is constructing the frequency table to determine the most common sentiment class. If 60% of reviews are labeled as positive, 25% as neutral, and 15% as negative, ZeroR will always predict positive for every review. This results in a baseline accuracy of 60%. With this benchmark in place, any machine learning model trained on this dataset must surpass 60% accuracy to be considered useful. If an advanced model struggles to outperform ZeroR, it indicates that the textual features extracted from the reviews may not be providing meaningful information. This suggests a need for improved text preprocessing, feature selection, or additional data enrichment. ZeroR also highlights the problem of class imbalance in sentiment analysis. If one sentiment category dominates the dataset, ZeroR's high accuracy might be misleading. It reveals that relying on accuracy alone is insufficient, and that metrics like precision, recall, and F1 score are necessary to assess how well a model captures minority classes, such as negative reviews. A model that predicts positive every time may achieve high accuracy, but will fail to capture customer dissatisfaction, which is often the most important insight for businesses. By comparing ZeroR's performance with more advanced text classification models, businesses can determine whether their approach to sentiment analysis is effective. If a model significantly outperforms ZeroR, it indicates that meaningful language patterns are being captured, leading to better insights into customer opinions. If ZeroR remains competitive, it signals that the model may not be extracting relevant features from the text and that further refinement is needed. ZeroR provides a foundational benchmark for sentiment classification, ensuring that machine learning models add real value rather than just introducing unnecessary complexity. Next, we'll examine how ZeroR fits into broader machine learning pipelines and how it helps evaluate model effectiveness. ZeroR is more than just a basic model. It plays a crucial role in machine learning pipelines by providing a baseline for model evaluation. In any classification task, ZeroR helps determine whether a more complex model is truly improving predictive performance or if it is simply adding unnecessary complexity. Understanding ZeroR's role in the broader machine learning workflow ensures that models are developed with meaningful improvements rather than just marginal gains. The first step in a machine learning pipeline is understanding the dataset. ZeroR helps with this by constructing a frequency table and identifying class imbalances. If one class significantly outweighs the others, ZeroR highlights this issue before any advanced modeling begins. This early insight can inform pre-processing decisions, such as whether resampling techniques are needed to balance the dataset. ZeroR is then used to establish a baseline accuracy. Suppose a dataset has 3 classes, with the most frequent class appearing 65% of the time. ZeroR's accuracy is therefore 65%. Any machine learning model trained on this dataset must outperform this benchmark to be considered useful. If an advanced model achieves only a slight improvement, it prompts a deeper evaluation of whether the model is capturing meaningful patterns or if the dataset lacks informative features. Beyond accuracy, ZeroR also reveals the need for more comprehensive evaluation metrics. In imbalanced datasets, ZeroR might achieve deceptively high accuracy while failing to detect minority classes. This emphasizes the importance of precision, recall, and F1 score when assessing model performance. If an advanced model improves accuracy but still neglects minority classes, it may not be much better than ZeroR in practical applications. Another key role of ZeroR is in guiding feature selection. Because ZeroR ignores all input variables, any improvement over its baseline must come from meaningful feature extraction. If a model barely surpasses ZeroR, it may indicate that the selected features are weak predictors of the target variable. This insight can lead to refinements in feature engineering, such as incorporating domain knowledge or using automated feature selection techniques. ZeroR is also useful in cross-validation. When models are tested on different subsets of data, ZeroR's performance can help assess whether results are consistent. If ZeroR achieves similar accuracy across multiple validation sets, but an advanced model fluctuates significantly, it suggests issues with overfitting or poor generalization. ZeroR acts as an anchor in machine learning pipelines, ensuring that models are improving in a meaningful way. It forces data scientists to justify complexity, refine feature selection, and use appropriate evaluation metrics. Without ZeroR, there would be no clear way to determine if a model is genuinely learning or just overcomplicating the problem. With ZeroR's role in model validation established, we now turn to its performance in imbalanced datasets, where its limitations become even more apparent. ZeroR operates under the assumption that predicting the majority class is the best approach, but this assumption quickly breaks down in imbalanced datasets. In many real-world classification problems, one class is significantly more frequent than the others, making ZeroR appear deceptively strong while failing to capture critical minority class instances. Understanding how ZeroR performs in these situations highlights why it is not suitable for many machine learning applications. Imbalanced datasets are common in fields like fraud detection, medical diagnosis, and rare event prediction. For example, in a medical dataset where 95% of patients are healthy and only 5% have a disease, ZeroR would predict healthy for every case, achieving 95% accuracy. At first glance, this seems impressive, but in reality, the model is completely useless. It never identifies the 5% of cases where the patient is actually sick. This failure exposes one of ZeroR's biggest flaws. It ignores minority classes entirely. The problem becomes even more apparent when considering evaluation metrics beyond accuracy. In imbalanced datasets, accuracy alone is misleading because a model can achieve high accuracy by simply predicting the dominant class. This is why alternative metrics such as precision, recall, and F1 score are crucial for assessing model performance. Precision measures how many of the predicted positive cases were actually correct, while recall measures how many actual positive cases were correctly identified. Since ZeroR never predicts the minority class, its recall for that class is always 0, making it ineffective in tasks where detecting rare events is critical. Another issue is that ZeroR provides an artificially high baseline in imbalanced datasets. If a dataset is 90% class A and 10% class B, ZeroR's accuracy will be 90% simply by always predicting class A. Any advanced model must outperform this, but the challenge is that small improvements in accuracy don't necessarily mean better performance in detecting the minority class. A model that achieves 91% accuracy might still miss most of the Class B cases, making it only marginally better than ZeroR in practical terms. To handle imbalanced datasets effectively, machine learning models must incorporate techniques such as resampling, cost-sensitive learning, or anomaly detection. Resampling involves either oversampling the minority class or undersampling the majority class to balance the dataset. Cost-sensitive learning assigns higher penalties for misclassifying the minority class, ensuring that models prioritize detecting rare events. Anomaly detection methods look for unusual patterns that indicate rare occurrences, rather than relying purely on frequency-based predictions. ZeroR's performance in imbalanced datasets underscores its primary limitation. It cannot differentiate between important and unimportant predictions. While it serves as a benchmark, it fails to provide useful insights when the minority class is the focus of analysis. This is why more sophisticated models must go beyond simple accuracy and consider the full range of performance metrics. Now that we've seen how ZeroR struggles with imbalanced data, let's explore how it compares to more complex classification approaches in different scenarios. ZeroR is often discussed in the context of simple baseline models. But an interesting aspect of its behavior is that it does not suffer from overfitting. Overfitting occurs when a model learns too much from the training data, capturing noise rather than meaningful patterns, and as a result fails to generalize to new data. Since ZeroR does not attempt to learn from input features, it is immune to this issue. However, this lack of overfitting comes at the cost of predictive power. Overfitting happens when a model is too complex for the dataset, memorizing specific details rather than identifying general trends. For example, a deep neural network trained on a small dataset might perform extremely well during training, but fail when tested on new data. ZeroR, on the other hand, never learns patterns. It simply predicts the most frequent class, meaning its performance remains consistent regardless of the dataset size or complexity. While avoiding overfitting might sound like a benefit, it is actually a reflection of ZeroR's fundamental weakness. Because it does not consider any input features, it cannot capture meaningful relationships between variables. This means that even when patterns exist in the data that could improve prediction accuracy, ZeroR ignores them entirely. It provides stability, but at the cost of effectiveness. This characteristic makes ZeroR a useful reference point when evaluating models for overfitting. If a complex model performs well on training data but struggles on validation or test data, it may be overfitting. Comparing its performance to ZeroR can help determine whether it is truly learning or just memorizing the dataset. If a model barely outperforms ZeroR on test data, it suggests that the added complexity is not providing real value. Another important aspect is that ZeroR does not contribute to variance in model predictions. Since it always predicts the same class, its results remain stable across different training runs. More complex models, however, can produce slightly different outcomes depending on how they are trained, the selection of hyperparameters, or random initialization of weights. This means that while ZeroR is a poor predictor, it provides a consistent benchmark that can be used to compare against more sophisticated models. Ultimately, ZeroR's inability to overfit highlights both its simplicity and its limitations. It is reliable in the sense that it will always yield the same results, but its usefulness is restricted to benchmarking rather than real-world application. It does not learn patterns, does not adapt to data, and does not offer insights, qualities that are essential for practical machine learning models. Now that we understand ZeroR's role in avoiding overfitting, let's explore how it can be used in data pre-processing to identify issues with class distributions and missing values. ZeroR may not be a powerful predictive model, but it plays a valuable role in data pre-processing. Before applying complex machine learning algorithms, it is essential to understand the structure of the dataset. ZeroR helps by highlighting key aspects of the target variable, such as class imbalances and missing values, allowing for better pre-processing decisions before moving on to more advanced models. One of the most important uses of ZeroR in data pre-processing is detecting class imbalances. Because ZeroR always predicts the majority class, its performance reflects the distribution of the target variable. If ZeroR achieves extremely high accuracy, it suggests that one class dominates the dataset. For example, in fraud detection, if ZeroR reaches 98% accuracy by predicting not fraudulent every time, it indicates that fraudulent transactions are extremely rare. This insight helps in deciding whether to use resampling techniques, cost-sensitive learning, or alternative evaluation metrics beyond accuracy. ZeroR can also help in handling missing values in classification problems. In datasets where certain records have incomplete information, a common strategy is to fill in missing target labels with the most frequent class. Since ZeroR already predicts the majority class, it provides a simple way to impute missing values in the target variable. While this is not always the best approach, it ensures that missing labels do not introduce unnecessary bias in the dataset. Another key role of ZeroR in data preprocessing is establishing a benchmark for data quality. If ZeroR performs nearly as well as more advanced models, it suggests that the input features may not be providing much additional predictive power. This forces a reassessment of the dataset. Are the right features included? Is the data clean and representative of real-world conditions? Does feature selection need improvement? By comparing advanced models to ZeroR, it becomes easier to spot issues with data quality early in the process. In some cases, ZeroR helps in identifying mislabeled data. If a dataset has inconsistent labeling, ZeroR may achieve unexpectedly high or low accuracy. For example, in sentiment analysis, if customer reviews labeled as negative contain highly positive language, it may indicate labeling errors. By analyzing ZeroR's performance, data scientists can flag potential inconsistencies and clean the data set before training more sophisticated models. While ZeroR does not contribute to learning in the traditional sense, its role in data preprocessing should not be overlooked. It provides an initial assessment of class distributions, highlights imbalances, offers a simple strategy for handling missing labels, and serves as a quality check before more complex models are applied. Now that we understand ZeroR's function in data preprocessing, let's move on to its broader benefits and limitations in classification tasks. ZeroR is often viewed as a trivial model, but it has a well-defined role in classification tasks. It serves as a baseline classifier for categorical data, providing a simple yet effective way to set a minimum performance benchmark. By always predicting the most frequent class, ZeroR establishes a reference point that other models must exceed to justify their complexity. While it lacks predictive power, its application in categorical classification problems helps in evaluating dataset characteristics and model performance. A common example of ZeroR in action is in customer satisfaction analysis. Suppose a dataset contains 3 satisfaction levels: satisfied, neutral, and dissatisfied. If 60% of responses are labeled as satisfied, ZeroR will predict this class for every instance, achieving a baseline accuracy of 60%. This allows data scientists to measure how much improvement more advanced classification models provide over a simple frequency-based approach. Another example is in product categorization. Consider a dataset where customers classify purchased items into categories such as electronics, clothing, and home goods. If electronics is the most frequently occurring category, ZeroR will classify all products as electronics, regardless of their actual attributes. While this method is clearly ineffective for real-world classification, it helps highlight imbalances in product distribution and serves as a comparison point for evaluating model improvements. One of the key benefits of ZeroR in categorical classification is its ease of implementation. Unlike decision trees, support vector machines, or neural networks, ZeroR requires no parameter tuning or feature selection. This simplicity makes it useful for quick model evaluation, particularly in exploratory data analysis, where the goal is to understand dataset distributions before applying more complex techniques. However, ZeroR's greatest limitation is its lack of differentiation between classes. In datasets where minority classes are crucial, such as fraud detection or medical diagnosis, ZeroR provides no meaningful predictions. For example, in a medical dataset where 90% of patients are healthy and 10% have disease X, ZeroR will always predict healthy, failing to identify any actual cases of the disease. This limitation makes it unsuitable for any scenario where detecting minority class instances is important. Despite its drawbacks, ZeroR's role as a baseline classifier remains significant. It acts as a control model against which other classification algorithms are measured. If a machine learning model does not substantially outperform ZeroR, it suggests that either the dataset lacks useful predictive features or the model is not properly designed. ZeroR is not a tool for making high-quality predictions, but rather a fundamental benchmark that ensures classification models add value beyond simple frequency-based guessing. With its role in categorical data classification established, we now explore how ZeroR applies to numerical data and its limitations in regression-based problems. ZeroR is primarily used for classification, but its concept can be extended to numerical data in certain contexts. When applied to regression tasks, where the goal is to predict a continuous numerical value rather than a discrete category, ZeroR follows a similar principle. It ignores all input features and instead predicts a single constant value based on the target variable. However, unlike classification, where ZeroR selects the most frequent class, in regression it predicts the mean average of the target variable. For example, in a dataset containing house prices, where the target variable represents home values in dollars, ZeroR would simply calculate the average price of all houses in the dataset and predict this value for every instance. If the dataset's mean home price is $250,000, ZeroR will predict $250,000 for every house, regardless of factors like location, size, or amenities. While this provides a baseline for model comparison, it is fundamentally flawed for real-world applications. House prices vary based on multiple factors, and predicting the same price for all houses disregards these essential differences. In this case, ZeroR is not useful for making actual predictions, but serves only as a benchmark to ensure that more advanced regression models add value. The main limitation of ZeroR in numerical data problems is its inability to capture relationships between variables. In classification, ZeroR already fails to consider features, but in regression, this problem becomes even more pronounced because numerical targets often depend on multiple input variables. If a linear regression or decision tree model barely outperforms ZeroR, it suggests that the dataset may lack strong predictive relationships or that additional feature engineering is needed. ZeroR's performance in numerical datasets is typically evaluated using error metrics such as mean squared error, MSE, or mean absolute error, MAE. Because ZeroR always predicts the mean, its error is based on how much individual values deviate from that mean. If an advanced model does not significantly reduce the MSE or MAE compared to ZeroR, it indicates that the model is not effectively learning from the data. Despite its shortcomings, ZeroR's use in numerical problems helps data scientists establish a baseline performance level for regression tasks. It allows for quick validation of dataset characteristics, ensuring that more advanced models provide meaningful improvements. However, unlike classification, where the majority class might still be a reasonable default prediction in some cases, ZeroR's mean-based approach in regression is rarely useful beyond benchmarking. ZeroR highlights the need for models that incorporate feature relationships and real-world variability in numerical predictions. With its role in both categorical and numerical classification defined, we now examine its place in ensemble learning and how it can be integrated into more complex model evaluation frameworks. ZeroR is often seen as a standalone baseline model, but it can also play a role in ensemble learning, where multiple models are combined to improve classification performance. While ZeroR itself is not predictive, It can be used as a reference point to assess the effectiveness of ensemble techniques and to ensure that complex models are providing real value. Understanding ZeroR's place in ensemble learning highlights its importance beyond just benchmarking. Ensemble methods such as bagging, boosting, and stacking are designed to improve classification accuracy by combining multiple weak or strong learners. ZeroR is sometimes included as one of the baseline models in these approaches, not for its predictive ability, but to compare whether ensemble methods are actually learning patterns in the data. For example, in a bagging-based ensemble like random forest, individual decision trees are trained on different subsets of the dataset. If the combined performance of these trees does not significantly outperform ZeroR, it suggests that the features being used are weak predictors, and the ensemble is not adding much value. ZeroR, in this case, acts as a control model, making sure that ensemble methods are genuinely improving upon the simplest possible prediction. In boosting algorithms such as XGBoost or AdaBoost, weak models are sequentially improved by focusing on misclassified instances. ZeroR provides a useful lower bound. If a boosting model struggles to exceed ZeroR's performance, it indicates that the boosting process is not effectively learning from the data. When comparing different classifiers within an ensemble, ZeroR can serve as a reference to filter out ineffective models. Many AutoML frameworks include ZeroR as one of the candidate models to establish a baseline before selecting and fine-tuning more complex algorithms. If a model's performance is close to ZeroR, it may be excluded from the ensemble since it is not contributing meaningful improvements. ZeroR is also useful in feature selection for ensembles. If ZeroR performs similarly to an ensemble method, it suggests that the selected features are not useful for classification. This can lead to refining the feature engineering process before applying ensembles, ensuring that only relevant features are used to build predictive models. While ZeroR helps benchmark ensemble methods, it is not directly useful as a contributing model in stacking or hybrid approaches. Since it always predicts the same class, it does not provide diversity in model outputs, which is crucial for ensemble learning. In most cases, ZeroR is used purely as a reference rather than an active component of the ensemble. ZeroR may not be a traditional machine learning model, but its role in ensemble learning ensures that advanced techniques provide genuine predictive improvements. By acting as a benchmark, ZeroR forces ensemble models to prove that their complexity is justified. Now that we've explored ZeroR's role in model selection, we move on to its interpretability and how it compares to more complex models in terms of transparency. One of ZeroR's defining characteristics is its simplicity, and with simplicity comes interpretability. Unlike complex machine learning models that require careful explanation and validation, ZeroR operates on a straightforward principle, always predicting the most frequent class. This makes it highly transparent, easy to understand, and free from hidden biases introduced by intricate algorithms. But while this simplicity makes ZeroR interpretable, it also limits its practical usefulness. ZeroR's logic is entirely transparent. It selects the most frequent class from the training data and predicts it for every instance. This means there is no room for ambiguity or unexpected behavior. Anyone, even someone with no machine learning background, can immediately grasp how ZeroR makes predictions. This makes it a useful teaching tool as well as a benchmark for understanding classification performance. Because ZeroR does not rely on input features, it avoids the complexity of feature weighting, variable interactions, and parameter tuning that make other models difficult to interpret. This is particularly useful in model transparency discussions where stakeholders need to understand why a model is making certain predictions. In contrast, more advanced models like deep learning networks often require explainability techniques, such as SHAP values or feature importance analysis to make sense of their outputs. In industries where model accountability is critical, such as healthcare, finance, and law, interpretability is a key concern. ZeroR being the simplest classification model, sets an understandable baseline against which more advanced models can be evaluated. If a complex model outperforms ZeroR but lacks transparency, decision makers may question whether the increase in accuracy is worth the trade-off in interpretability. ZeroR provides a reference point to assess whether a model's complexity is justified. ZeroR also helps in validating data assumptions. If a complex model does not perform significantly better than ZeroR, it suggests that the input features may not be contributing meaningful information. This forces data scientists to reassess their data preprocessing, feature selection, and modeling approach. While ZeroR is fully transparent, its lack of decision-making power limits its usefulness in real-world applications. Unlike interpretable models such as decision trees, which provide clear rules for classification, ZeroR provides no insights into the relationships between features and outcomes. This makes it unsuitable for tasks where understanding why a decision was made is just as important as the decision itself. Additionally, in scenarios where multiple factors influence predictions, such as medical diagnoses or risk assessments, ZeroR fails to provide any explanatory power. While a logistic regression model might show that certain symptoms increase the likelihood of a disease, ZeroR provides no such insights. It simply predicts the most common diagnosis without considering any patient characteristics. ZeroR is the most interpretable classification model, but this interpretability comes at the cost of usefulness. It is best used as a benchmark rather than a predictive tool, ensuring that more complex models provide both improved accuracy and meaningful insights. While transparency is valuable, real-world applications require models that both perform well and explain their decisions. With ZeroR's role in interpretability established, we now explore its relevance in educational settings and how it is used to teach fundamental machine learning concepts. ZeroR may not be a powerful predictive model, but it serves an important role in machine learning education. Because of its simplicity, ZeroR is often one of the first models introduced to students and professionals learning about classification problems. It provides an easy-to-understand foundation for concepts such as baselines, class distributions, and model evaluation. By studying ZeroR first, learners can better grasp more complex machine learning models when they are introduced later. One of the first lessons in machine learning is understanding the importance of baseline models. ZeroR demonstrates that before applying sophisticated algorithms, it is necessary to establish a simple benchmark. Students learn that a complex model is only valuable if it outperforms a basic approach like ZeroR. If a machine learning model barely exceeds ZeroR's performance, it suggests that the model is not learning useful patterns. This concept is particularly useful in exploratory data analysis, EDA. By running ZeroR on a dataset, students can quickly identify issues such as class imbalances, poor data quality, or the need for better feature selection. This helps reinforce the idea that data preprocessing and feature engineering are just as important as model selection. ZeroR is also an excellent tool for teaching classification performance metrics. Since ZeroR always predicts the most frequent class, its accuracy is easy to calculate. Students can compare this baseline accuracy with metrics such as precision, recall, and F1 score. This helps illustrate why accuracy alone is not always the best evaluation metric, especially in imbalanced datasets where ZeroR may appear to perform well while completely ignoring minority classes. Another key educational benefit of ZeroR is that it clearly highlights the limitations of naive models. By demonstrating how ZeroR ignores all input features, students can see firsthand why feature selection and proper model tuning are necessary. It also helps introduce the concept of bias-variance trade-off, as ZeroR represents an extreme case of high bias and low variance. Furthermore, ZeroR is often compared with slightly more advanced models such as 1R, one rule, which selects a single feature to make predictions instead of ignoring them entirely. By moving from ZeroR to 1R, students gain an appreciation for the role of input features in machine learning. ZeroR is widely used in introductory machine learning courses because it can be implemented with just a few lines of code. Whether using Python, R, or Weka, students can quickly test ZeroR on different datasets, observe its accuracy, and compare it with other models. This hands-on approach makes it easier to understand the process of building and evaluating classification models. Additionally, ZeroR is often used in data science competitions and AutoML platforms as a reference model. Students participating in these challenges learn to measure their model's effectiveness by ensuring it performs significantly better than ZeroR before refining their approach. ZeroR plays a valuable role in machine learning education by serving as a baseline model for classification problems. It teaches students about performance evaluation, the importance of data preprocessing, and the limitations of simplistic approaches. By understanding ZeroR first, learners gain a stronger foundation for working with more advanced models. With its role in education established, we now examine ZeroR's final significance, its place in historical and theoretical discussions of machine learning models. ZeroR operates on a straightforward principle. It predicts the majority class of the target variable without considering any input features. While its simplicity might seem like a limitation, it's precisely this quality that makes ZeroR an essential tool in the early stages of machine learning projects. When the goal is to establish a quick, clear baseline, ZeroR is often the first model to turn to. It provides insights that are critical for evaluating whether a problem is worth pursuing and sets the stage for more advanced techniques. At its core, ZeroR strips machine learning down to the bare minimum. It doesn't analyze features, doesn't search for relationships, and doesn't tune parameters. It simply selects the most frequent class. This simplicity makes it an ideal starting point for any model development process. When you're faced with a new data set, the first question to ask is, what's the easiest prediction I can make? ZeroR answers this question by offering an immediate, no-frills prediction based purely on the target variable. For example, in a dataset where 70% of customers are classified as satisfied and 30% as unsatisfied, ZeroR will always predict satisfied. The result? A quick benchmark accuracy of 70%. This gives you an immediate sense of the dataset's class distribution and establishes a minimum standard that all future models must exceed. If an advanced algorithm barely outperforms ZeroR, it suggests that there's a deeper issue, either with the dataset or the modeling approach. One of ZeroR's greatest strengths is how easy it is to implement. There's no need for complex algorithms, training loops, or hyperparameter tuning. All it takes is a single calculation to determine the most frequent class in the dataset. This makes ZeroR incredibly accessible, even to those new to machine learning. Its simplicity ensures that time is not wasted on unnecessary complexity at the start of a project. In the context of prototyping, this efficiency is invaluable. Let's say you're building a model to predict customer churn. By applying ZeroR, you immediately establish a benchmark. Perhaps 80% of customers don't churn, so ZeroR predicts no churn with 80% accuracy. This gives you a clear starting point for evaluating whether additional effort in feature selection or algorithm development is justified. If a more advanced model achieves 82% accuracy, it might not be worth the additional complexity. Conversely, if the new model reaches 90%, the value of your improvements becomes evident. ZeroR also acts as a mirror for the data itself. If the accuracy of ZeroR is unexpectedly high, it could indicate a heavily imbalanced dataset. For instance, in fraud detection, if 98% of transactions are legitimate and only 2% are fraudulent, ZeroR will predict legitimate every time, achieving 98% accuracy. While this may look impressive on the surface, it reveals a potential challenge: the need to address the minority class more effectively. ZeroR highlights these imbalances, providing valuable guidance for the pre-processing phase. Additionally, ZeroR forces practitioners to ask whether their input features actually add value. If a model with all available features barely outperforms ZeroR, it signals that the features are not providing meaningful information. This can lead to revisiting the dataset, improving feature engineering, or even reconsidering the problem's framing. The role of ZeroR extends beyond being a simple baseline. It's a tool for prioritization. By providing a quick and easy way to assess performance, ZeroR helps data scientists focus on what matters most. If a dataset yields poor results even when evaluated against ZeroR, it suggests that the problem may not be suitable for machine learning, saving time and resources early in the process. On the other hand, if ZeroR performs reasonably well, it provides a solid foundation to build upon. Future iterations can focus on incorporating features, testing algorithms, and refining predictions, all while using ZeroR as a reference point for evaluating progress. ZeroR might not be flashy or sophisticated, but its value lies in its simplicity. It cuts through the noise, providing a clear starting point for any classification task. By establishing a minimum benchmark and exposing potential issues in the data, ZeroR serves as a compass, guiding practitioners toward more effective solutions. In the fast-paced world of prototyping, where decisions need to be made quickly, ZeroR ensures that every step forward is based on a solid foundation. Its straightforward approach reminds us of an important lesson. Before chasing complex models, make sure the basics are covered. ZeroR gives you that foundation, a reminder that even in machine learning, sometimes less is more. ZeroR may seem like a trivial model, but its application reveals much more than just baseline predictions. Its simplicity brings to light critical aspects of data quality that often go unnoticed. By solely relying on the majority class for predictions, ZeroR allows us to assess whether the dataset itself is providing meaningful insights. Understanding how ZeroR interacts with data quality can highlight potential flaws, ensuring better preparation for advanced models. ZeroR operates by predicting the most frequent class in the target variable, disregarding all predictor variables. This straightforward behavior makes it a powerful diagnostic tool. If ZeroR achieves high accuracy, it might suggest that the dataset is heavily imbalanced, with one class dominating the others. This serves as an immediate warning that advanced models might also over-rely on the majority class unless the imbalance is addressed. For instance, in customer satisfaction data, where 80% of responses are satisfied, ZeroR would predict satisfied for all cases, achieving an 80% accuracy. However, this accuracy says little about the dataset's ability to capture nuances in customer behavior. It also highlights that without addressing the minority class, e.g. dissatisfied, the model risks failing to identify meaningful trends. The performance of ZeroR is directly tied to the quality of the dataset. High-quality data ensures that ZeroR's frequency-based predictions are accurate representations of the target class distribution. However, when data quality is poor due to missing values, mislabeled data, or noisy inputs, ZeroR's predictions can become skewed, masking underlying issues. Consider a dataset with missing or incorrect labels. If satisfied responses are overcounted due to mislabeling, ZeroR will incorrectly assume this is the majority class, leading to misleading predictions. Similarly, if important classes are underrepresented because of sampling bias, ZeroR might fail to highlight the dataset's true distribution. These scenarios emphasize the need to validate the data before relying on ZeroR or any other model. ZeroR also struggles with datasets that include frequent but irrelevant categories. For example, in spam detection, if the dataset is dominated by non-spam emails, ZeroR's high accuracy might hide the fact that it never detects spam correctly. This underscores the importance of thorough data cleaning and preprocessing before using ZeroR as a baseline. Data validation is critical when using ZeroR as it ensures the reliability of the dataset and its outputs. By validating the data, checking for class imbalances, resolving missing values, and correcting mislabeled entries, you can enhance ZeroR's utility as a baseline model. This process ensures that ZeroR reflects the true structure of the dataset, making its predictions meaningful and actionable. For example, a frequency table analysis during data validation can help identify whether the majority class is disproportionately large. Techniques such as resampling or synthetic data generation, e.g., SMOT, can then be applied to balance the dataset, ensuring that advanced models outperform ZeroR in meaningful ways. ZeroR's simplicity makes it an excellent tool for uncovering hidden data issues. If ZeroR's accuracy is unexpectedly high or low, it might indicate problems such as class imbalances. If one class dominates the dataset, ZeroR will highlight this by achieving high accuracy without learning. Mislabeled data. If ZeroR's predictions don't align with expectations, it may suggest labeling inconsistencies. Inadequate features. If advanced models fail to outperform ZeroR, it could indicate that the input features lack predictive power. These insights can save valuable time by guiding early corrections in the data pipeline before significant resources are invested in model development. ZeroR's relationship with data quality is both revealing and practical. Its reliance on the majority class exposes flaws in the dataset such as imbalances, labeling errors, or missing values. By validating and improving the data before moving to more complex models, you can ensure that every step in the machine learning process is built on a solid foundation. ZeroR is not just a baseline, it's a lens through which the true nature of your data becomes visible. By starting with ZeroR, you can uncover and address critical data quality issues, setting the stage for meaningful and accurate predictions. ZeroR, despite its simplicity, holds a valuable place in academic and applied machine learning research. Its role extends beyond being a basic classifier. It serves as a foundation for understanding model performance, evaluating methodologies, and guiding advancements in the field. In research, where rigor and reproducibility are critical, ZeroR provides clarity and structure, ensuring that every new development is meaningfully benchmarked. ZeroR's primary function in research is as a baseline model. By predicting the majority class, it establishes the minimum expected accuracy for any classification task. This is particularly useful when evaluating new algorithms or methodologies. If a proposed model cannot outperform ZeroR, it calls into question the value of the approach. This makes ZeroR an indispensable tool for ensuring that progress in machine learning is both measurable and significant. For example, in research on customer churn prediction, ZeroR might predict that no customers will churn, achieving an accuracy of 75%. If a new model achieves only 76% accuracy, researchers must investigate whether the additional complexity is justified or if the data itself lacks predictive power. ZeroR provides the clarity needed to make these critical evaluations. ZeroR is often used as a reference point for comparing advanced classification algorithms. Its simplicity offers a stark contrast to complex models, highlighting their strengths and weaknesses. Researchers use ZeroR to measure how much value each additional layer of complexity adds to a model. For instance, in studies comparing decision trees, support vector machines, and deep learning models, ZeroR's performance sets the baseline. A decision tree that achieves 80% accuracy compared to ZeroR's 70% might demonstrate solid performance. However, if a deep learning model reaches only 81%, researchers might conclude that the added complexity of deep learning does not justify the marginal improvement over simpler approaches. This comparative analysis also extends to feature selection. By showing that ZeroR's performance is close to that of a model using all features, researchers can identify which features contribute little or no predictive power. In academic research, ZeroR is frequently included in studies to validate the effectiveness of proposed methodologies. Its inclusion ensures that any observed improvements in accuracy are meaningful rather than coincidental. By serving as a baseline, ZeroR reinforces the importance of methodological rigor in machine learning. For example, in a study on imbalanced datasets, ZeroR might highlight the dominance of the majority class. Researchers can then test resampling techniques, cost-sensitive learning, or anomaly detection methods to demonstrate how these approaches improve upon Zero's naive predictions. Without this comparison, it would be challenging to assess the true impact of the proposed solutions. ZeroR also plays a critical role in reproducibility. By providing a simple, standard benchmark, it ensures that research results can be consistently evaluated across different studies and data sets. This makes ZeroR a foundational tool in academic work, fostering transparency and comparability. The reliance on ZeroR in research underscores the importance of model evaluation and the need for robust performance metrics. ZeroR challenges researchers to critically assess their models, ensuring that they contribute valuable insights beyond what can be achieved with a basic classification approach. In practical terms, this means that ZeroR often prompts researchers to revisit the fundamentals. If a complex model struggles to outperform ZeroR, it raises questions about the dataset, feature engineering, or even the framing of the problem itself. This iterative process leads to more robust and meaningful model development. ZeroR's role in research goes far beyond its function as a simplistic classifier. It provides a baseline against which all other models are measured, ensuring that advancements in machine learning are both significant and meaningful. By establishing a clear standard for performance, ZeroR fosters methodological rigor, comparative analysis, and reproducibility, making it an indispensable tool in the pursuit of better models and insights. In research, as in practice, ZeroR reminds us that meaningful progress begins with understanding the fundamentals. ZeroR may be a simple baseline model, but its utility extends into practical business scenarios, particularly as a benchmark for assessing more complex models. In business applications where decisions are guided by data, ZeroR plays a supporting role in ensuring that predictive models genuinely add value. By providing a clear and reliable baseline, it helps organizations evaluate whether their machine learning strategies are effective and aligned with their objectives. In business contexts, the value of a predictive model often hinges on whether it outperforms the simplest possible approach. ZeroR provides a straightforward baseline by predicting the most frequent class, allowing companies to measure whether more sophisticated models are worth their complexity. For example, in customer retention analysis, ZeroR might predict that every customer will remain loyal if the majority class in the dataset represents non-churners. This establishes a baseline accuracy, say 85%, against which more advanced models must compete. If a machine learning model achieves only 86% accuracy, it may not justify the additional costs in computation, implementation, and maintenance. ZeroR ensures that decision makers are not swayed by marginal improvements that fail to deliver tangible business value. Retail sector. In retail, ZeroR can be used to quickly estimate customer behavior by identifying the most commonly purchased product category. For instance, if 60% of transactions involve electronics, ZeroR will predict that every customer purchase will fall into this category. While this is not a nuanced prediction, it can provide a quick starting point for inventory planning or sales forecasting, especially when time or resources are constrained. Healthcare analytics. In healthcare, ZeroR can predict the most frequent diagnosis in patient records, offering a baseline for understanding demographic trends. For example, if 70% of patients are diagnosed with a common flu, ZeroR would predict this diagnosis for all cases. While insufficient for clinical decisions, this insight can inform resource allocation, such as ensuring sufficient staffing or supplies for most common conditions. These examples demonstrate that ZeroR, while simplistic, can provide actionable insights in settings where quick approximations are needed before deploying more advanced solutions. Effectiveness. ZeroR is particularly useful in scenarios with heavily imbalanced target classes. By predicting the majority class, it offers a quick snapshot of the dataset structure and serves as a reliable benchmark for evaluating the performance of complex models. This is especially valuable in tasks like fraud detection, where identifying the dominant non-fraudulent class provides immediate context for further analysis. Limitations. Despite its utility as a baseline, ZeroR cannot capture relationships between variables or provide meaningful predictions in nuanced scenarios. For instance, in demand forecasting or risk assessment, ZeroR's inability to incorporate input features makes it unsuitable for real decision-making. Businesses that rely solely on ZeroR risk missing critical patterns that drive their operations, such as changes in customer preferences or emerging trends. ZeroR's role in business applications extends to guiding the selection and development of predictive models. If a model cannot significantly outperform ZeroR, it signals that either the data lacks predictive power or the model requires improvement. This early insight can save organizations time and resources, redirecting efforts toward more effective strategies. For example, if a customer segmentation model achieves only marginal improvements over ZeroR, it might indicate that the features used are not informative. This feedback can lead to a deeper exploration of customer behaviors, better feature engineering, or the inclusion of external data sources. ZeroR serves as a foundational tool in business applications, helping organizations assess the effectiveness of their predictive models and ensuring that resources are directed toward meaningful improvements. While it is not a solution in itself, ZeroR provides a reliable benchmark that supports better decision-making, sharper model evaluation, and more strategic use of machine learning in business contexts. By starting with ZeroR, businesses can ensure that their models add value, turning insights into actionable outcomes. ZeroR's simplicity makes it an essential component in predictive analytics, particularly as a starting point for benchmarking and model evaluation. While ZeroR lacks the complexity of advanced algorithms, it plays a vital role in establishing a baseline that ensures any subsequent model delivers meaningful improvements. In predictive analytics, where actionable insights drive decision-making, ZeroR serves as a guiding light for evaluating the relevance and value of models. ZeroR functions as a foundational benchmark in predictive analytics by predicting the most frequent class without considering input features. This establishes a minimum accuracy threshold that more advanced models must surpass to be deemed useful. By setting this baseline, ZeroR allows analysts to measure whether the effort and resources invested in a model are justified. For example, in demand forecasting, ZeroR might predict that the majority product category, say electronics, will account for all future sales. If an advanced forecasting model improves accuracy only marginally, it prompts a reevaluation of whether the model adds value. ZeroR's role here is to expose inefficiencies and ensure that resources are allocated toward meaningful innovations. Additionally, ZeroR helps identify the strength of the underlying dataset. If a predictive model performs only slightly better than ZeroR, it suggests that the dataset lacks predictive features or that the relationships between variables are weak. This feedback guides analysts to refine their data collection or feature engineering processes before proceeding with more complex modeling. ZeroR's simplicity makes it a valuable companion to more sophisticated algorithms, offering a baseline against which their incremental value can be measured. This comparative role ensures that advanced models are genuinely leveraging the data to provide better predictions. Complementary role. ZeroR often works alongside advanced models to assess their performance improvements. For instance, in a classification task where ZeroR achieves 70% accuracy, a decision tree that reaches 85% can be evaluated for its contribution beyond the baseline. If a deep learning model reaches only 86%, it highlights diminishing returns in complexity compared to simpler models. Enhancing predictive accuracy. Understanding how well ZeroR performs can also lead to better model tuning. If an advanced model struggles to outperform ZeroR, it indicates that further feature selection or parameter adjustments may be required. This insight ensures that predictive analytics efforts are focused on improving the model's ability to extract actionable insights. In predictive analytics, the goal is not just to achieve high accuracy, but to ensure that models provide value in real-world scenarios. ZeroR sets a clear standard, challenging analysts to demonstrate that their models outperform naive predictions. By serving as a baseline, ZeroR reinforces the importance of metrics such as precision, recall, and F1 score, especially in tasks involving imbalanced datasets or critical decision-making. For instance, in customer retention analysis, ZeroR might predict that no customers will churn, achieving high accuracy in a heavily imbalanced dataset. However, this prediction offers no actionable insights for retaining customers. Advanced models must therefore exceed ZeroR's performance in ways that directly contribute to strategic outcomes. ZeroR is more than just a simplistic model. It's a benchmark that ensures predictive analytics efforts are grounded in measurable value. By setting a foundational baseline, it forces analysts to justify the complexity of their models and ensures that predictive insights are actionable and impactful. While ZeroR alone cannot drive decision-making, its role in benchmarking and model evaluation makes it a cornerstone of responsible and effective predictive analytics. ZeroR's simplicity doesn't just make it a baseline model, it also provides a unique starting point for understanding and visualizing data. By focusing on the majority class and ignoring input features, ZeroR allows practitioners to assess class distributions and prediction performance visually. This clarity is particularly valuable when analyzing datasets or communicating findings to non-technical stakeholders. Data visualization, paired with ZeroR, bridges the gap between raw data and actionable insights. One of the key aspects of ZeroR is its reliance on a frequency table, which lists the count of occurrences for each class in the target variable. Visualizing this table helps illustrate the class distribution in an intuitive way, making it easier to identify imbalances or dominant classes. For example, a bar chart displaying the frequency of 3 classes, satisfied, neutral, and dissatisfied, can quickly show that satisfied dominates the dataset with 70% of the data. This visual representation highlights ZeroR's prediction strategy and sets the stage for comparing its performance with more complex models. Such visualizations are particularly useful in exploratory data analysis, EDA, where understanding the dataset structure is crucial before applying predictive algorithms. ZeroR's performance can also be visualized by comparing its predicted values with actual outcomes. Using tools like a confusion matrix, practitioners can observe how many instances ZeroR correctly classifies as the majority class and where it fails. This comparison provides insight into the limitations of ZeroR and sets expectations for what advanced models need to achieve. For instance, if ZeroR predicts satisfied for all cases, but the actual labels show significant numbers of dissatisfied customers, the confusion matrix will clearly highlight these misclassifications. This visual representation not only shows ZeroR's weaknesses, but also underscores the need for more nuanced models that address minority classes effectively. Another powerful application of ZeroR in data visualization is benchmarking with performance metrics. Visualizing metrics like accuracy, precision, recall, and F1 score helps compare ZeroR with more advanced models. Line graphs or bar charts can illustrate how these metrics improve as models increase in complexity. For example, if ZeroR achieves an accuracy of 70% on a dataset, a bar chart can compare this baseline with the performance of a decision tree, 85%, and a neural network, 90%. This visual progression highlights the incremental improvements brought by each model, providing a clear narrative for stakeholders. Such visualizations are particularly helpful in demonstrating the value of model development efforts. They make it easy to show how much better advanced models perform compared to the baseline, ensuring that decision makers understand the impact of machine learning investments. Here are the benefits of visualization in ZeroR analysis. Clarity in class distributions. Visualizing ZeroR's frequency table makes it easier to identify imbalances and dominant classes in the dataset, highlighting misclassifications. Tools like confusion matrices provide a clear picture of where ZeroR falls short, guiding improvements in data preprocessing and model design. Communicating model progress. Charts comparing ZeroR with advanced models make it easy to demonstrate the value of feature selection, algorithm choice, and parameter tuning. ZeroR's simplicity makes it a powerful tool for data visualization, enabling practitioners to uncover patterns and communicate results effectively. By visualizing class distributions, prediction results, and performance metrics, ZeroR helps bridge the gap between data exploration and decision-making. It sets the stage for advanced models to shine while ensuring that stakeholders have a clear understanding of the data and the value of machine learning efforts. In predictive modeling, as in storytelling, clear visuals often speak louder than complex algorithms. Model validation is a cornerstone of effective machine learning, and ZeroR plays a vital role in this process. As a baseline classifier, ZeroR ensures that every step in model development is rooted in measurable progress. Its simplicity allows for quick evaluations, providing a clear benchmark for assessing the validity and reliability of more advanced models. By understanding how ZeroR contributes to model validation, we can better design systems that are robust, reliable, and impactful. ZeroR acts as a fundamental checkpoint in model validation. By predicting the most frequent class, it provides a simple yet powerful baseline for evaluating performance. If an advanced model fails to significantly outperform ZeroR, it indicates potential issues with the dataset, feature selection, or model design. This ensures that machine learning efforts are not wasted on overfitting unnecessary complexity or datasets with weak predictive signals. For instance, in a dataset where 80% of customers are classified as satisfied, ZeroR's prediction of satisfied establishes a baseline accuracy of 80%. Any machine learning model applied to this dataset must exceed this accuracy to be considered valid. Without ZeroR, it would be difficult to determine whether a model's performance is genuinely meaningful or simply an artifact of the dataset's distribution. One of ZeroR's key contributions to model validation is helping to set clear performance standards. By establishing a minimum threshold for accuracy, ZeroR ensures that any improvements brought by advanced models are measurable and justifiable. For example, if a new algorithm achieves 80% accuracy on the same dataset, the 2% improvement over ZeroR must be scrutinized. Is the improvement statistically significant? Does it justify the added complexity? ZeroR forces these questions to be addressed, promoting a disciplined approach to model evaluation. Additionally, ZeroR helps in identifying cases where performance metrics beyond accuracy are necessary. In imbalanced datasets, ZeroR's high accuracy might mask poor performance in minority classes. This highlights the need for metrics such as precision, recall, and F1 score to evaluate models more comprehensively. ZeroR also plays a role in ensuring the reliability of predictive models. By providing a consistent baseline, it enables comparisons across different datasets, algorithms, and experiments. If a model performs worse than ZeroR, it signals deeper issues that must be resolved before deployment. For instance, in fraud detection, ZeroR might predict that all transactions are legitimate, achieving high accuracy due to the rarity of fraud. If a fraud detection model fails to improve on ZeroR, it indicates that the model is not capturing meaningful patterns. This insight ensures that unreliable models are caught early, preventing costly mistakes in real-world applications. ZeroR also aids in validating the robustness of advanced models. By using ZeroR as a baseline, practitioners can test whether their models generalize well across different subsets of data. If an advanced model's performance varies significantly across subsets, it suggests overfitting or instability, while ZeroR's performance remains steady as a control. Model validation is an iterative process, and ZeroR provides a foundation for continuous improvement. Each iteration of feature engineering, algorithm selection, or hyperparameter tuning can be evaluated against ZeroR to measure progress. This feedback loop ensures that every change contributes to a model that is both accurate and reliable. For example, in customer segmentation, initial attempts at clustering might only slightly outperform ZeroR. By iterating on feature engineering, such as incorporating purchase history or demographic data, practitioners can incrementally improve performance using ZeroR as a reference to measure meaningful gains. ZeroR's role in model validation is critical for ensuring that machine learning systems are both effective and reliable. By setting a baseline, it helps establish performance standards, highlight weaknesses in data or models, and promote disciplined, iterative development. While ZeroR itself is not a predictive solution, its simplicity ensures that every step in the machine learning process is grounded in measurable progress. With ZeroR as a starting point, organizations can build models that are robust, impactful, and aligned with their goals. Cross-validation is a vital process in machine learning, ensuring that models generalize well to unseen data and are not overfitted to the training set. While ZeroR is a simplistic baseline model, it plays a role in this process by establishing a performance benchmark during cross-validation. ZeroR's results in cross-validation provide a point of comparison, helping practitioners identify whether their models are genuinely learning or simply overfitting. Cross-validation allows for a deeper evaluation of a model's reliability by splitting the dataset into multiple subsets, training the model on some subsets, and testing it on others. When applied to ZeroR, cross-validation serves two main purposes: establishing a baseline. ZeroR's accuracy across different folds of the dataset provides a minimum benchmark. If an advanced model fails to outperform ZeroR consistently in cross-validation, it suggests that the model is either poorly designed or the dataset lacks predictive power, validating model reliability. Since ZeroR's predictions are based solely on the majority class, its performance remains steady across folds. This stability provides a point of comparison to evaluate whether more complex models are producing consistent results. For example, in a 5-fold cross-validation setup, ZeroR might achieve the same accuracy across all folds, e.g. 75%, reflecting the majority class distribution. Advanced models, in contrast, may show variability in performance across folds. If this variability is significant, it raises questions about the model's robustness. To integrate ZeroR into a cross-validation process, follow these steps: data splitting. Divide the dataset into K subsets, folds, use K1 subsets for training, and the remaining subset for testing. Model training. Train the ZeroR model on the training folds. Since ZeroR requires no feature input, this step simply involves calculating the majority class in the training data. Performance evaluation. Test ZeroR on the remaining fold, recording its accuracy. Repeat this process for each fold, then average the results to obtain a robust performance estimate. These steps provide a systematic way to assess ZeroR's baseline performance across the dataset, ensuring that its results are consistent and reflective of the overall class distribution. ZeroR's performance in cross-validation offers a critical reference point for evaluating more complex models. If a sophisticated model struggles to outperform ZeroR, it indicates that features are not informative. The input features may lack predictive power, requiring further engineering or exploration. Overfitting is occurring. The model might be too complex for the dataset, capturing noise rather than meaningful patterns. Dataset is imbalanced. A heavily skewed target variable may lead advanced models to mimic ZeroR's behavior by overpredicting the majority class. For example, in an imbalanced classification task like fraud detection, ZeroR might achieve 98% accuracy by predicting no fraud for all cases. If an advanced model achieves similar accuracy but fails to improve recall for fraudulent transactions, cross-validation results can highlight this limitation, prompting adjustments to the modeling approach. ZeroR's role in cross-validation extends to guiding model selection and improvement. By consistently comparing model performance against ZeroR, practitioners can identify which algorithms and features contribute the most value. This iterative approach ensures that the final model is not just complex, but also effective and reliable. For instance, if ZeroR achieves 70% accuracy and a decision tree achieves 80% in cross-validation, the 10% improvement justifies further refinement of the decision tree. Conversely, if a deep learning model achieves only 72%, it prompts reconsideration of whether the added complexity is warranted. ZeroR's integration into cross-validation highlights its value as a benchmark for assessing model performance and reliability. By providing a stable and predictable baseline, ZeroR ensures that machine learning efforts are grounded in measurable progress. Its role in cross-validation not only supports model evaluation, but also helps identify areas for improvement, guiding the development of more robust and impactful models. With ZeroR, practitioners can approach cross-validation with confidence, knowing they have a clear reference point for success. ZeroR plays a surprisingly insightful role when it comes to feature engineering. By acting as a baseline that relies only on the majority class, ZeroR provides an invaluable reference point for evaluating the impact of the features added to a dataset. It ignores input features entirely, predicting the majority class in the target variable. This simplicity makes it a perfect benchmark for understanding the value of features. Before adding complex features or tweaking algorithms, comparing performance against ZeroR ensures that any improvement is genuinely due to better inputs or better modeling. If ZeroR achieves 70% accuracy in a binary classification problem where 70% of the data belongs to one class, any improvement beyond that indicates that the added features are enhancing predictive capabilities. Feature engineering often starts with identifying which variables contribute the most to a model's predictive power. ZeroR sets the bar low but clear. If a model with added features does not outperform ZeroR, it signals that those features may not be useful or that they're not being utilized effectively by the model. This role is particularly important in early experimentation. Consider a dataset where the majority class dominates and initial engineered features fail to add value. ZeroR's performance acts as an immediate diagnostic tool, prompting analysts to rethink their approach. ZeroR also helps gauge the effectiveness of feature engineering. A significant performance boost over ZeroR suggests that the engineered features are contributing valuable information to the predictions. On the other hand, a marginal improvement could highlight inefficiencies in feature selection or the need for further refinement. For example, if a model achieves only 72% accuracy compared to ZeroR's 70%, it prompts a deeper dive into the features. Are they redundant, irrelevant, or poorly scaled? ZeroR provides the clarity needed to ask these questions. Imagine a customer segmentation task where ZeroR predicts the majority class, such as high-value customers, with 60% accuracy. After adding demographic and behavioral data, if the model accuracy jumps to 85%, it's a clear signal that the features are enhancing predictions. Conversely, if the accuracy remains close to 60%, it suggests that the features are not contributing effectively, and further engineering or exploration is required. ZeroR may be simple, but its role in feature engineering is profound. It establishes a reliable, no-frills benchmark, helping practitioners assess whether the time and effort spent on feature creation are truly paying off. By leveraging ZeroR as an initial yardstick, you ensure that every added feature is justified and contributes meaningful value to the final model. ZeroR simplicity meets strategic insight, creating a foundation for smarter, more effective modeling. ZeroR, as one of the simplest classification models, brings a unique perspective when discussing hyperparameter tuning. In most machine learning models, hyperparameters are critical. They can be fine-tuned to optimize performance, control overfitting, and ensure stability. However, ZeroR bypasses this entire concept due to its simplicity, providing a baseline without the need for any adjustments or optimizations. Hyperparameter tuning is a process used to adjust parameters that are not directly learned from the data, such as the depth of a decision tree or the number of hidden layers in a neural network. For ZeroR, this process is irrelevant because there are no parameters to tune. The model operates solely by predicting the majority class, eliminating any complexity. This lack of tunable parameters highlights the essence of ZeroR as a benchmark rather than a predictive tool. The absence of hyperparameter tuning underscores an important aspect of ZeroR's design. It exists to serve as a starting point. By offering a simple static performance baseline, it shifts the focus to the incremental improvements provided by more sophisticated models. If a model that has undergone extensive hyperparameter optimization performs worse than ZeroR, it signals a deeper issue with the dataset or feature selection. The simplicity of ZeroR also reinforces the importance of choosing appropriate algorithms. While ZeroR cannot be optimized, more advanced models require careful tuning to ensure they surpass its baseline. ZeroR's static nature emphasizes that the added complexity of these models must lead to tangible improvements, justifying the additional computational resources and time spent. By serving as a baseline, ZeroR provides clarity. It isolates the impact of hyperparameter tuning in other models, highlighting whether the optimization process is genuinely enhancing predictive performance or merely overfitting to the training data. ZeroR ensures that any gains are meaningful and not the result of unnecessary complexity or random noise. ZeroR, despite its simplicity, offers a valuable lesson in restraint. In a field where tweaking and optimizing parameters can consume significant effort, ZeroR reminds practitioners to step back and consider whether the improvements justify the additional complexity. By providing a no-optimization benchmark, it ensures that hyperparameter tuning efforts remain grounded in practicality and purpose. Deploying machine learning models often involves complex steps, including data preparation, model integration, and performance monitoring. ZeroR simplifies this process by stripping away unnecessary complexity, serving as a foundational benchmark to evaluate other models before committing to deployment. Its simplicity makes it particularly relevant in environments where quick integration and reliability are critical. ZeroR begins by constructing a frequency table for the target class, identifying the most frequent value as the prediction. This straightforward mechanism ensures clarity during deployment, Unlike advanced models that may require extensive feature engineering or algorithm tuning, ZeroR's deployment process focuses on its ability to establish a baseline for more sophisticated models. The deployment process for ZeroR is efficient. It involves cleaning and preprocessing the dataset to ensure accurate frequency calculations, followed by integrating the ZeroR model into a production environment. This can include embedding it in existing systems or creating an API endpoint to facilitate real-time predictions. ZeroR's computational simplicity ensures compatibility with diverse platforms and minimal resource requirements. Once deployed, monitoring ZeroR's performance becomes essential. By regularly comparing its predictions to those of more advanced models, practitioners can assess the effectiveness of added complexity. Accuracy tracking allows for clear insights into whether deployed models outperform the ZeroR baseline. If a model consistently performs below this threshold, it signals the need for further refinement or adjustments. Maintaining a deployed ZeroR model involves periodic updates to adapt to new data. As datasets evolve, recalibrating the frequency table ensures that predictions remain relevant. Additionally, error analysis helps identify scenarios where ZeroR may underperform, providing valuable feedback for designing future iterations. ZeroR's simplicity does not diminish its utility in the deployment phase. Instead, it highlights the importance of establishing a solid foundation. By acting as a benchmark, ZeroR ensures that subsequent deployments of more advanced models are grounded in measurable improvements, reducing the risk of overcomplicated or ineffective solutions. ZeroR simplifies deployment while setting the stage for reliable, performance-driven machine learning systems. In environments where speed is crucial, ZeroR's simplicity makes it an effective choice for real-time predictions. Its straightforward approach of predicting the majority class allows it to deliver results almost instantaneously, making it suitable for use cases where time is of the essence and decisions must be made rapidly. ZeroR operates by constructing a frequency table for the target variable and selecting the most frequent class as its prediction. This simplicity translates directly into speed, as the model does not require complex calculations or feature evaluations during runtime. Once deployed, ZeroR can provide predictions in real time with minimal computational overhead, ensuring seamless integration into systems that demand high responsiveness. This efficiency makes ZeroR particularly relevant for environments with limited computational resources or where quick insights are necessary. For instance, in monitoring systems or initial filtering tasks, ZeroR can serve as a lightweight solution to provide immediate outputs before more advanced models take over for deeper analysis. However, while ZeroR excels in speed, its limitations become apparent in dynamic and rapidly changing environments. Because it relies solely on historical data to identify the majority class, it lacks the ability to adapt to shifts in data patterns or recognize nuances in real-time inputs. This limitation means ZeroR may struggle in scenarios where understanding relationships between variables or adapting to new trends is critical. Despite these challenges, ZeroR's role in real-time predictions is not to replace more sophisticated models, but to act as an initial step. By providing a quick and reliable baseline, ZeroR ensures that systems can handle time-sensitive tasks efficiently, while more advanced solutions are implemented in parallel. ZeroR's value in real-time applications lies in its balance of simplicity and speed. It offers a practical option for delivering immediate results, ensuring that processes dependent on timely decision-making are not delayed. While it may not provide deep insights, ZeroR remains a dependable tool for foundational tasks, bridging the gap between speed and accuracy in real-time machine learning workflows. In the realm of big data, where the scale and complexity of datasets can be overwhelming, ZeroR offers a unique advantage with its inherent simplicity and scalability. Its reliance on basic frequency calculations makes it an efficient choice for handling vast amounts of data, especially in scenarios where establishing a baseline performance metric is critical. The scalability of ZeroR stems from its minimal computational requirements. Unlike more complex models that demand significant resources to process large datasets, ZeroR's straightforward approach allows it to scale seamlessly. By constructing a frequency table and selecting the most common class as its prediction, ZeroR can process extensive datasets quickly without the need for feature evaluation or algorithmic optimization. This makes it ideal for initial analysis or rapid benchmarking in big data contexts. Performance is another area where ZeroR shines in big data scenarios. While it does not provide detailed insights or nuanced predictions, it serves as a critical baseline against which more complex models can be measured. For example, when testing new algorithms on a large dataset, comparing their performance to ZeroR helps determine whether the added complexity is justified. If a sophisticated model does not outperform ZeroR, it raises questions about the effectiveness of its design or the quality of the data. ZeroR's simplicity also facilitates faster deployment and iteration in big data projects. Its lack of dependency on features or hyperparameters means that it can be quickly implemented to provide immediate insights. This agility is valuable in fast-paced environments where quick decisions are necessary, such as real-time monitoring systems or exploratory data analysis. Despite its strengths, ZeroR's limitations remain evident in big data contexts. Its inability to capture relationships between variables or adapt to changing data trends means it is not suitable for tasks requiring deep insights or predictive accuracy. However, as a foundational tool, ZeroR's role is not to replace advanced models, but to complement them by providing a clear benchmark and ensuring that complex approaches deliver meaningful improvements. In big data applications, ZeroR proves that simplicity can be a strength. By offering an efficient, scalable, and reliable baseline, it helps organizations navigate the challenges of large-scale data while maintaining clarity and focus on what truly adds value. ZeroR's simplicity and computational efficiency make it an ideal candidate for deployment in cloud computing environments. Its lightweight nature allows seamless integration with major cloud platforms like AWS, Google Cloud, and Microsoft Azure, offering scalability and accessibility for various machine learning workflows. Cloud platforms provide a flexible infrastructure for deploying and running ZeroR models. By leveraging these platforms, data scientists can quickly implement ZeroR to benchmark model performance without requiring extensive setup or resource allocation. For example, AWS SageMaker and Google Cloud AI offer built-in tools that make deploying ZeroR for classification tasks straightforward, enabling organizations to evaluate the performance of more complex models in a cost-effective way. One of the most significant benefits of ZeroR in cloud computing is its ability to serve as a baseline for advanced systems. By offering a clear performance benchmark, ZeroR ensures that the complexity of other models deployed on the cloud is justified. For instance, a team testing a neural network on Google Cloud can compare its results to ZeroR's baseline to determine if the added computational cost is yielding meaningful improvements. ZeroR's lightweight structure also translates into cost efficiency. It requires minimal computational power, which reduces cloud processing costs, especially for large-scale tasks. This makes it a practical choice for quick iterations, early-stage model testing, or use cases where speed and simplicity are paramount. However, ZeroR's limitations also come into play. While it integrates easily into cloud workflows, its lack of predictive power means it cannot handle complex datasets or uncover intricate patterns. This restricts its utility to benchmarking and initial testing, leaving more nuanced predictions to advanced models. Despite these challenges, ZeroR's role in cloud computing is significant. By combining simplicity with scalability, it offers organizations a way to streamline model deployment, benchmark effectively, and reduce costs. Whether it's providing a foundational baseline or acting as a stepping stone for more sophisticated approaches, ZeroR remains a valuable asset in leveraging the full potential of cloud-based machine learning solutions. In an era where data privacy is a central concern, ZeroR offers a unique advantage due to its simplicity and limited reliance on input features. By predicting the majority class without considering predictor variables, ZeroR inherently reduces the risk of exposing sensitive or personal data. Its straightforward mechanism aligns well with the principles of data minimization, a cornerstone of modern data privacy regulations. The minimalistic design of ZeroR ensures that no personal or identifiable information is processed during prediction. This makes it a practical choice for organizations aiming to comply with stringent data protection laws, such as GDPR or CCPA. By focusing only on the target variable's distribution, ZeroR sidesteps the complexity of managing sensitive features, which could otherwise increase the risk of data breaches. However, the simplicity of ZeroR also has implications for data security. While it minimizes the handling of sensitive data, its oversimplified approach can lead to incomplete insights. For instance, if critical predictors are ignored in a dataset, ZeroR might overlook key patterns that advanced models could use to strengthen security measures. This limitation highlights the importance of understanding ZeroR's scope. It provides a safe foundation but may not always offer the nuanced intelligence required in sensitive applications. ZeroR also raises ethical questions in data privacy. As organizations strive to balance transparency with predictive accuracy, ZeroR demonstrates how simpler models can help address privacy concerns without sacrificing the integrity of the system. For instance, its use in ethical AI frameworks can set a standard for transparency, ensuring that predictions are both fair and explainable. As data privacy regulations continue to evolve, ZeroR serves as a reminder of the value of simplicity. By adhering to principles of minimal data processing and reducing reliance on sensitive information, it highlights a path forward for developing machine learning models that respect privacy while maintaining utility. Future research into combining ZeroR with advanced privacy-preserving techniques such as federated learning could further enhance its role in secure, compliant AI systems. ZeroR's minimalistic approach underscores the possibility of achieving data privacy and compliance without unnecessary complexity. By aligning with the values of transparency, safety, and efficiency, it provides a valuable foundation for building responsible and privacy-conscious machine learning frameworks. ZeroR's simplicity and transparency position it as an important tool in the pursuit of ethical artificial intelligence. By relying on a straightforward principle, predicting the majority class without considering input features, it eliminates the complexity that can sometimes obscure how predictions are made. This transparency makes it easier for stakeholders to understand its operations, which is crucial in building trust and accountability in AI systems. However, ZeroR's reliance on the majority class introduces potential for bias, particularly in datasets with imbalanced distributions. For example, if a dataset heavily favors one class, ZeroR will perpetuate this imbalance, potentially marginalizing minority classes. This highlights an ethical challenge. While ZeroR is transparent, it risks reinforcing existing inequalities when used in decision-making processes without careful consideration of dataset composition. Ethical implications extend to its use in applications where fairness is critical. ZeroR's inability to consider nuanced relationships between variables means it cannot address or correct biases present in the data. For instance, in hiring algorithms or loan approvals, relying solely on ZeroR would overlook important individual factors, leading to outcomes that may not be equitable. Despite these limitations, ZeroR serves a valuable role in benchmarking ethical AI practices. By setting a baseline performance level, it ensures that more advanced models demonstrate measurable improvements in both accuracy and fairness. For example, a model that outperforms ZeroR while addressing bias and providing explainable predictions shows a clear progression toward ethical standards. ZeroR also encourages a focus on simplicity in AI. Its clear operations provide a model of how transparency can be prioritized without sacrificing functionality. This approach can inspire the development of more advanced algorithms that maintain explainability while tackling complex ethical challenges. In the broader context of ethical AI, ZeroR's limitations act as a guide for improvement. Its use underscores the importance of addressing biases in data, ensuring fairness in predictions, and building trust through transparency. By understanding ZeroR's role and its boundaries, practitioners can use it as a stepping stone toward developing models that uphold the principles of equity, accountability, and integrity in artificial intelligence. All right, let's talk about ZeroR and automated machine learning, AutoML. Think of it this way, you're building a skyscraper. Before you go all in on fancy glass walls and rooftop gardens, you need a strong foundation. That's ZeroR. It's your starting point, your baseline, your how low can we go for model performance. Without it, you're basically guessing if your fancy models are doing anything worthwhile. Here's the deal. ZeroR is like that super honest friend who keeps you grounded. It's simple. It predicts the majority class in your data. That's it. No magic, no algorithms, just a straight up, I think the most common thing is the answer. And this makes it the perfect benchmark in AutoML frameworks. Imagine you're building a fraud detection model. ZeroR might predict that 90% of transactions are not fraudulent. If your shiny, complicated model can't beat that, yeah, you got some work to do. ZeroR is here to keep it real, to make sure your improvements aren't just noise. Now, AutoML platforms like Google AutoML H2O.ai or Azure ML love ZeroR. Why? Because it helps them sort the wheat from the chaff. These tools run dozens, sometimes hundreds, of models on your data. ZeroR is the no-nonsense baseline. If a model performs worse than ZeroR, it's basically telling you, hey, this isn't adding any value. Think of it like this. ZeroR is the bar your models need to clear to even enter the competition. It's the minimum viable performance. Without it, you might end up with complex models that do a lot of nothing. Here's where it gets interesting. ZeroR acts as the first filter. Imagine you're hiring someone, and ZeroR is the pre-screening test. Any candidate, or in this case, model, that doesn't pass gets cut. Only models that perform better move forward. It's like a reality check. If a model can't outperform ZeroR, why waste time on it? This ensures you're not just building complex systems for the sake of complexity, but actually adding meaningful predictive power. But let's be honest, ZeroR isn't the hero of the story. It's more like the guard at the door. It doesn't care about trends, relationships, or patterns in your data. It's just there to say, this is your baseline. Beat it or go home. Think of ZeroR like training wheels on a bike. It's great when you're starting out, but if you're still relying on it down the road, you're not going to win any races. The real work happens when you take what you've learned and build something better. If your AutoML model isn't significantly outperforming ZeroR, it's time to take a step back. Check your data. Look at your features. Are they actually relevant? Maybe the problem isn't your model, it's what you're feeding it. ZeroR is basic, but it's brilliant. It's not here to win any awards. It's here to make sure every step you take is a step forward. So next time you're using AutoML, don't skip this step. Use ZeroR as your reality check. And hey, if you've got any stories about ZeroR saving your project or slapping you with some hard truths, drop them in the comments. Let's keep the conversation going. Buckle up. We're diving into ZeroR and industry standards, the unsung hero of keeping things fair, measurable, and professional in machine learning. Picture this. Industries like healthcare, finance, and marketing need to make sure their models are solid, reliable, and measurable. Enter ZeroR, the baseline that keeps everyone honest and ensures models meet a minimum level of accuracy. ZeroR is like the referee in a sports game. It sets the rules and ensures fair play. By acting as the most basic classifier, it establishes a baseline for model performance across industries. Think of it this way. If your fancy fraud detection algorithm or your patient readmission model can't outperform ZeroR, you've got some serious rethinking to do. Imagine a hospital using a machine learning model to predict patient outcomes. ZeroR might say, let's assume every patient falls into the most common category like non-critical. If your model doesn't do better than that, it's basically useless and potentially dangerous. ZeroR ensures models add real value and aren't just overcomplicating things. Now, here's the beauty of ZeroR. It's the ultimate benchmark. It's not just about saying, this is good enough. It's about creating a standard that's easy to understand and measure. Think of it as the starting line in a race. Your advanced models, whether they're neural networks, decision trees, or random forests, are the runners. ZeroR stands at the start, waving the flag and saying, beat this line or you're not even in the game. This is especially critical in industries where decisions based on these models can have huge implications. If a credit risk model, for instance, fails to outperform ZeroR, it means the bank might as well rely on basic historical data instead of wasting time and resources on an ineffective algorithm. Now let's talk compliance. Industries are big on regulations. Think GDPR in Europe or HIPAA in healthcare. ZeroR aligns beautifully with these regulations. Its simplicity means it adheres to principles like data minimization and transparency. You're not doing anything fancy with sensitive data, just using it as a benchmark. And here's the kicker. Using ZeroR isn't just about hitting regulatory checkboxes. It's about demonstrating that your machine learning process is thorough, auditable, and justifiable. Companies can confidently say, our model is better than the baseline, and here's the proof. Want to impress stakeholders or regulators? Start by showing them ZeroR as your baseline. It sets the stage for how your advanced model adds value, and it's way easier to explain than deep neural nets. So, why does ZeroR matter for industry standards? Because it keeps machine learning grounded. It ensures that no matter how advanced or complex your model is, it's actually worth the effort. ZeroR is the line in the sand, the point every model needs to surpass to prove its value. Now, let's hear from you. What's the toughest benchmark your model has faced, and how did it compare to ZeroR? Drop a comment below and share your stories. Think of ZeroR as the foundation of a skyscraper. As we build higher, adding complexity, sophistication, and power, ZeroR remains the unshakable baseline. But what if this foundation starts playing an active role in future applications? Imagine integrating ZeroR with advanced algorithms, for instance. As models become more complex, ZeroR can act as a checkpoint, helping researchers measure the incremental value added by each new feature or layer. This isn't just about validation, it's about optimization. ZeroR ensures we're not just throwing complexity at problems for the sake of it. And here's a hot trend: benchmarking in automated machine learning, AutoML. AutoML tools are becoming the go-to for businesses to generate predictive models. ZeroR fits in here like a glove. It serves as a default benchmark in AutoML frameworks, ensuring that any automated model produced by these tools surpasses the most basic level of accuracy. Now let's talk real-world scenarios. As datasets grow messier and more imbalanced, ZeroR becomes a lifesaver. Picture a medical dataset where the majority class is non-critical patients. ZeroR says, hey, let's just predict that everyone falls into this majority category. This might sound overly simplistic, but it's a great starting point to measure if your new model is truly improving predictions for minority classes like critical patients. It shines in handling data imbalance. And let's not forget education. As machine learning becomes a cornerstone of education, ZeroR will continue to be the ultimate teaching tool. It's simple, intuitive, and perfect for explaining the concept of baselines in predictive modeling. ZeroR doesn't just prepare future data scientists for the real world. It ensures they understand the importance of foundational thinking. When working on a new model, start by implementing ZeroR. It gives you an immediate sense of what your data can do at its most basic level. Plus, stakeholders love seeing how far you've come from the baseline to the breakthrough. The future of ZeroR isn't about replacing advanced algorithms, it's about complementing them. Whether it's serving as a benchmark in cutting-edge AutoML systems, helping with data imbalance, or simplifying education, ZeroR is here to stay. It's a reminder that even as machine learning pushes boundaries, we must never lose sight of the basics. Now, let's hear from you. How do you think ZeroR will evolve in the next decade? Do you see it playing a bigger role in your projects? Let me know in the comments below. Let's bring it all together with a crisp summary of ZeroR, the unsung hero of classification models. If you've been following along, this is the perfect moment to sit back and connect all the dots. Ready? Let's go. Definition. At its core, ZeroR is as simple as it gets. It's a fundamental classification model that predicts the majority class in a dataset while completely ignoring the predictor variables. It's like saying, let's go with the most common answer for now. Working mechanism. How does ZeroR work? Imagine you're looking at a dataset with two target classes. 70% belong to class A and 30% to class B. ZeroR doesn't bother analyzing the inputs. It simply constructs a frequency table, picks class A, and predicts it for every instance. No frills, just raw simplicity. Advantages. Here's why ZeroR is loved and often underestimated. Baseline benchmarking. It sets the floor for performance. Any model that can't beat ZeroR, well, back to the drawing board. Simplicity. It's easy to implement, requiring minimal resources, and gets you started quickly when working with new datasets. Limitations. Of course, simplicity comes at a cost. ZeroR's predictive power is nearly zero, making it ineffective for datasets with significant variability. And if the majority class isn't representative of your data, relying on ZeroR can lead you down the wrong path. It's not a crystal ball, it's a ruler to measure against. Practical applications. So where does ZeroR shine? Preliminary data analysis. It's perfect for quickly gauging the performance of your dataset before you bring in the big guns. Baseline for sophisticated models. It ensures that any model you create is genuinely predictive and not just overly complex noise. ZeroR may not solve all your machine learning problems, but it's the foundation every data scientist needs. Whether you're benchmarking, analyzing imbalanced datasets, or teaching ML fundamentals, ZeroR is always the first step towards success, and there you have it. ZeroR, simple, powerful, and foundational. So tell me, what's your favorite use case for ZeroR? Drop it in the comments. I'd love to hear your thoughts.